Hello everyone, welcome to day 19 of Advent of Code. Today's problem was very neat. Part 1 was a simulation of sequential matching with arithmetic conditions. The parsing was the most intricate we've seen so far this year, and while the matching procedure was straightforward, it was also something we hadn't encountered before. Part 2 then required us to compute ahead of time the ranges of numbers that would make it through the matching procedure. It took a bit of symbolic logic and range operations to write. All in all, it was a very fun problem to solve. As always, this video has chapters so that you can skip around, and the link to the code is in the description below. Now, without further ado, let's get started. Day 19. Aplenty. The elves of Gear Island are thankful for your help and send you on your way. They even have a hang glider that someone stole from Desert Island. Since you're already going in that direction, it would help them a lot if you would use it to get down there and return it to them. I'm pretty sure this was us, pretty sure we stole that glider earlier. As you reach the bottom of the relentless avalanche of machine parts, you discover that they're already forming a formidable heap. Don't worry though, a group of elves is already here organizing the parts, and they have a system. How are there even elves here? This was a barren wasteland filled with ghosts. To start, each part is rated in one of 4 categories. X, extremely cool looking. M, musical, it makes a noise when you hit it. A, aerodynamic, presumably it flies well if you throw it, and S, shiny, presumably it glints in the sun. Then each part is sent through a series of workflows that will ultimately accept or reject the part. Each workflow has a name and contains a list of rules. Each rule specifies a condition where to send the part if the condition is true. The first rule that matches the part being considered is applied immediately, and the part moves on to the destination described by the rule. The last rule in each workflow has no condition and always applies if it reached. Hold on, this looks like a pipeline with match statements, or just a match statement. So each part is sent through a series of workflows that will ultimately accept or reject the part. Each workflow has a name and contains a list of rules. Each rule specifies a condition and where to send the part if the condition is true. Okay, yeah, this looks like a chain of match statements. Consider the workflow. X, curly brackets. X is greater than 10, 1. M is less than 20, 2. A is greater than 30, R. And A. This workflow is named X and contains 4 rules. If workflow X were considering a specific part, it would perform the following steps in order. Rule. X greater than 10, 1. If the part's X is more than 10, send the part to the workflow named 1. Rule. M less than 20, 2. Otherwise, if the part's M is less than 20, send the part to the workflow named 2. Otherwise, if the part's A is more than 30, the part is immediately rejected, R. Otherwise, because no other rules match the part is immediately accepted. Also, it's not match statements, it's more like a graph of processing. And each part has all 4 of these attributes. So parts aren't just X or M. They have a certain value for X and a certain value for M, and one for A and one for S. If a part is sent to another workflow, it immediately switches to the start of that workflow instead and never returns. If a part is accepted, sent to A, or rejected, sent to R, the part immediately stops any further processing. In fact, this all reminds me very much of NetFilter firewall rules. This is exactly how IP tables, IP chains, and NF tables works. The system works, but it's not keeping up with the torrent of weird metal shapes. The elves ask you if you can help sort a few parts and give you the list of workflows and some part ratings, your puzzle input, for example. Okay, so we have a bunch of rules in the format above, then we have a bunch of parts. The workflows are listed first, followed by a blank line, then the ratings of the parts the elves would like you to sort. All the parts begin in a workflow named in. In this example, the 5 listed parts go through the following workflows. Where's in? This is our starting workflow. So this part, it goes in, then S is not less than 1351. Right, S is not less than 1351, so it goes into QQZ. QQZ. S is greater than 2770, so it goes into QS. QS. S is not greater than this, so we go into LNX. LNX. And LNX. M is greater than 1548, so we accept. Ultimately, 3 parts are accepting. Adding up the X, M, A, and S rating for each one of the accepted parts gives 7540. For the part with this, adding all of the ratings for all the accepted parts gives the sum total of 19,114. So sort through all the parts you've been given. What do you get if you add together all the rating numbers for all the parts that ultimately get accepted? Oh, this actually seems easy. Or rather, this seems straightforward to code, if a bit annoying to parse. Let's look at our full input. The input doesn't look all that big. There aren't that many rules, and there aren't that many parts. What would happen if we had a loop? If we had a loop, we'd never escape it, so presumably we have no loops. And since the parts are all different, there's no caching to be done, as in the branches. There's no optimization or memoization to be done. We just have to run the parts through the rules and see what we get. Okay, let's start. Parsing is going to be a bit challenging, but I think we can do this. Yeah, this seems doable. We're not going to use a parser combinator library because the Elixir ones are a bit, let's just say, special. And I'm much more comfortable with just using regular pattern matching. Alright. So plan. We are going to parse the input, then apply the rules, and that should be it for part 1. So now we just have to run our parts through the rules and see which are accepted. Now we have to add up the parameter values and then add up everything else. That's the right answer. You are 1 gold star closer to restoring snow operations. Yes, this was much nicer than yesterday's. Part 2. Even with your help, the sorting process still isn't fast enough. One of the elves comes up with a new plan. Rather than sort parts individually through all these workflows, maybe you can figure out in advance which combinations of ratings will be accepted or rejected. Each one of the 4 ratings can have an integer value ranging from a minimum of 1 to a maximum of 4,000. All possible distinct combinations of ratings. Your job is to figure out which ones will be accepted. In the above example, there are a very large number of distinct combination ratings that will be accepted. Consider only your list of workflows. The list of part ratings that the elves wanted you to sort is no longer relevant. How many distinct combinations of ratings will be accepted by the elves' workflows? Alright, so first off, if this is the number for the example, this is larger than the number we can iterate through. Yes, we can normally do about maybe 10 million operations per second in Elixir, and this is what, millions, billions, trillions, it's 167 trillions. So we can definitely not just try all the possible combinations for these parameters and see if they go through the workflows or not. We instead have to do something with sets again. So let's take our example input and let's think about this. So we'll be going, we always start with rule in. So the order here doesn't actually matter. What matters is that we start with rule in. And then all the part combinations that have s less than 1351 go to PX. Otherwise, everything else goes to QQZ. In other words, QQZ is the list of parts where S is greater or equal to 1351. Okay, let's say we got S less than 1351 and got into PX. Here. To go into PQQ, we have to do A less. We also have to have the A less than 2006 restriction. And then we go into QKQ and here. And then if X is also less than this number, then we accept. So to get to this accept here, well, one way to get to this accept here is to have S less than 1351, A less than 2006, and then X less than 1416. So this will be something like 2 or 3 million combinations. So one way to do this would be to start from the top and then compute the list of conditions that must be true to go into each of the chains. Let's start calling these chains. So we start in the int chain. Then to get into the PX chain, we add this condition. Then to go into the QKQ chain, we add this condition. And then so on and so on. Then if we do this, we can then take all of our A's and presumably compute the number of possible parts that satisfy those conditions. Now, notably, we're doing this the wrong way around, because if we do this, we also will end up inevitably, like here, we inevitably end up with a part with a chain that ends in a reject condition, or it ends in a reject answer. So this is a bit wasteful. So the alternative would be to start from the bottom and then work our way up. Right? So for instance, to get to this A, we know that X has to be less or equal than this. And then so S also has to be greater or equal to this. And then we work our way up until we reach in. But this seems harder to do. And this is ultimately just a speed optimization. So let's try our top-down approach first, and then if this isn't fast enough, we go and do the bottom-up approach instead. So top-down, we are going to start in, and then we are just going to accumulate conditions and follow the chains until we get to A's, and then we are going to list all of the conditions for each of the A's. I want to try this out to make sure that it actually works. Yeah, let's do that. So instead of compute constraints here, let's call something else. Let's say this is mostly good. Let's say data is part1.read example. No, it's saying negate doesn't exist. So let's do negate first. Negate of a condition. And our conditions our condition looks like this, and we want to our condition is this, so we want to negate it. So negate of then value is going to be less than or equal param value. Of less than param value is going to be greater than or equal param value. I don't think we need to be able to negate these as well. We should never actually hit them. Okay, data is unused. Where? Line 6. So here's one place. Yeah, sure. Back is unused. Yeah, we will use it afterwards once we actually write this. Okay, so we have data. Let's now call compute rule constraints and see what happens. We're going to call this on in. Let's start with in. So it's .roots.in. Constraint so far is empty, and the accumulator is empty. This is saying I'll inspect the rules. Okay. I'll inspect the rules of in actually. Right. So it's saying that to get into QQZ, you have to be greater than or equal to S3051, which is correct. Or to get into PX, you have to be less than S1351. Okay, this looks right. So far, let's save these and let's call it again for QQX and see what happens. QQZ. So far, and our accumulator is empty. Strings. Okay, this is more complicated. Let's here, I'll inspect the rules for QQZ as well. Okay, so to get into, let's start with QS. To get into QS, you have to be greater than S, greater. Which one are we doing? We're doing QQZ. So you have to be greater or equal to S1351. This was the rule from the first step. Oh, this is wrong. This should not say, there should not be a name here. Something's, where is it? This one is incorrect. This one is adding. shouldn't add target? What's the result of IO inspect so far? Okay, so this is correct, but then there shouldn't be any, there shouldn't be any names here. These names aren't helpful. So the condition somehow is getting something wrong in it. The condition is somehow getting a target. Oh, which it makes sense that it's getting a target because, yeah, it makes sense that the condition is getting a target. But we don't, that just confuses our output. So here, let's just say condition is delete condition. Condition shouldn't have a target. No, but it's getting it from here. Because so far contains these things. So far isn't right. So far here, I actually should call so far of so here. So far is actually going to be a map. So far here is so far of QQZ. Better. So to get into, let's start with QS. To get into QS, you have to be greater than 2770, yes, and you also have to be greater than or equal to S1351, which is the condition from the first one. Get into HDJ, you have to be greater than or equal to 351, which is the base case, or the condition from the previous chain. Then you have to be less than or equal to 2770, because it didn't match this one. And then you also have to be less than this. Okay, this is correct. And then to R, you have one extra condition, right? Rather, you have the flip of this condition. Okay, this works. Now let's somehow write this into here. it's saying that the way to get to these terminations is with these conditions. And we just now have to count how many, we just now have to take all of the A's and count how many possibilities this sort of condition actually generates. So first off, let's print this out nicely because this is a bit unreadable. So these are now our constraints. Let's print them out so that it's nice. Commas here. Okay, so it's saying to get one way to get to A is, so one way to get to A is M greater than 2090, A greater or equal to 2006, and S less than 351. Is that true? I don't know. I'll inspect some more stuff. What do we want to do? Here we return data. We do another then. Okay. So to get to this A, we have to, it's something M greater than 2090. How did we do that? Here. M greater than 2090, we go into A. So to get to here, we have to also be greater than or equal to A 2006. Greater than or equal to A 2006. And to get to here, we had to be in the PX. How did we get to PX? Where's in? Here. So to get into PX, we had to be S less than 351. S less than 351. Okay, I'm going to boldly claim that this is correct. But now we need to compute how many parts can possibly can match these conditions. How many parts match these conditions? Actually, hold on. Can we do this for full? Or will it be too slow? Because the next step is just a bit of arithmetic, which will always be fast. But the question we had earlier is our top-down approach too slow? It is not. It computed in 93 milliseconds. All right, back to example. So we don't need this. We still have the constraints here. Let's compute how many possibilities match the constraints. That's what we have to do, right? Of all the possible distinct combination of ratings, your job is to figure out which ones will be accepted. The above example, there are this many distinct combinations of ratings that will be accepted. say def combinations a constraint. Then we take all of our conditions and we will output a number for them and then multiply the numbers. The condition is always up param value. But no, this is not quite right. We also have to group by parameter name first. And so for instance here, we first have to group all of the m's together. Yes, we have to group all of the m's together and then do something with this. So before we compute conditions, let's do some more work on these values. Yeah, let's call this group conditions. Up parameter value, then parameter up value. Into isn't quite what we want. So inserts the given enumerable into a collectible according to the transformation function. Also not quite what we want. Let's do it manually. Reduce. We start with an empty map. Get condition, an accumulator. Here. Do update in other map.put accumulator. Not called name, this is called param. Param. Add addition constant to map.get. Pack param empty list as a default. See if this worked. We have our constraints. Actually pipe this through group constraints. Group conditions. Pulling argument. This has to be in an app. Okay, so here's what we now get. We get A and then have just one condition for it. Then S and two conditions. I'm looking for a bigger one. Surely, yeah, there's one with 3. So here, this S is to be greater than or equal to 3051, and also greater than 27270, and also greater than 3448. Now we have to do range operations, and because we know the full range, it's 1 to 4000. Have to take 1 to 4000 and then pass it through these rules and then see what we get. And just do this with numbers because 4000 is a small enough number that we can literally just do it with ranges. Okay, so after group conditions, we're going to do count possibilities. Possibility is just going to take one of these lists. So conditions. So we're going to do 1 to 4000 dot filter conditions. Filter and now we do this is start with conditions, then we do an enum reduce. Up value. Possibilities. Then we're just going to run possibilities do an enum.filter and just going to case up to. Okay, so this is less than, then n has to be less than value. And this gives us our new possibilities. Then we just do a length, other length. Let's compile, it does compile. Now, after we've done group conditions, we are going to map over the conditions. So this is going to be a nested map. Here we do enum.map. .map. So have these things. Now we have a name here. This is going to be name and conditions. Map the conditions to different possibilities. Conditions. Constraints here. Conditions was better. Conditions. Conditions. And possibilities. Okay, so now it's saying that to get into this A, there are this many possibilities for A, this many possibilities for M, and so on. So it's about time we filtered out all of the R's. So let's just do this here. .filter and .reject. This gives us just the A's. Okay. Now here, instead of returning haram, should we just okay, let's see if it works. Care about the parameter. Right. Now we do dot product. We get a bunch of numbers, and now if we do enum.sum, we have to get rid of the A's. Here we don't return name, we just return the number. This is our final number, 829, which is very different from this. Frustrating. So I guess we're going to debug this with a smaller example. I'm going to add more intermediate state first, and then we're going to debug it with a more complex example. So let's undo a few of the things we just did. Interestingly, we also got a much smaller number than them. So it's not that we're overcounting, we're undercounting massively somehow. All right, so start. Let's group conditions again. Group conditions gives us this stuff. Random question, but is count possibilities correct? So here we get A less or equal to 1716. So it should be 1716. 1716, fine. M is, I see what we're doing wrong here. Look, some of the numbers, some of the parameters are completely unbound here. As in, sure, we have restrictions here on A, M, and S, but not on X. So X could there should be an X 4000 here. So in group conditions, we need to ensure that we have condition for each one. So in group conditions here we go. This is actually not going to be an empty set. This is going to be A. These are strings, aren't they? They're almost certainly strings. A, M, S, X. Should actually be this syntax since those aren't atoms. Call this the unconstrained. And if now we now have more of these. Good. So it blew up here. This is not a list. This is not a list. Go over possibilities. So no, we reduce over conditions. It's saying conditions is not a list. Well, it indeed isn't. It's a num.toList. Now here. This is inefficient because we're generating a bunch of lists of 4,000 elements, but hey, it's probably fine. Okay, and now much better. We have conditions, all of our conditions, all of our constraints now also have these unconstrained values. All right. Let's give names to these things. So let's say grouped. What's this one? Oh, this one is called counted. Actually, no, this one is called non-possibilities. Plus possibilities. Okay, so these are our possibilities, and now we want to actually do the multiplication thing. So here, we're going to do, what do we call this? We start with possibilities, then we do a new map, get a name, which is always A, so we don't care about it, get conditions. Take the conditions. Actually, we take, this is possibilities, count possibilities. Possibilities. Then we map. This is going to give us parameter, which we don't care about, a num. Possibilities. We're just going to return num possibilities. Let's inspect this. Okay, we get this. So now here we do a product. Okay, these look like bigger numbers. And now here we do a new dot sum. Okay, 167. 167. This looks good. 167, 409, 67, 409, 079, 079, 868, and then 3 zeros. 868 and then 3 zeros. Okay, this looks correct. Let's try this on full and see if we get the right answer. This is a big number. That's the right answer. You are 1 gold star closer to restoring snow operations. Yes, good. This was a lot easier than yesterday. I mean, it took a bunch of coding, but Even the reasoning wasn't all that hard today. Okay, let's quickly clean up all of the IO inspects. Let's just return the possibilities and be done. Now this should just return the one number, which is your advent calendar, 19. And it's still this answer. Still this number, yes. Variable data is unused. Where? Okay, yep, we do not need data anymore. We also don't need this stuff. Okay, and that's it. Should we draw a visualization for this? It would be kind of neat to have an actual graph to display, but it isn't required. It would help with my thumbnail later. Although the trouble with drawing a visualization today is that it has to be a graph, so it has to be mermaid charts with ArtStack. And mermaid charts are always kind of horrible. Well, let's give it a shot. Worst case, we end up drawing a useless visualization. So, let's get going. We start with the input. We want to draw this crap. We want to draw the rules. We want to draw the rules. And we need... How does this work? This is going to generate an edge between CRN and A. And the text on the edge is going to be x greater than 2662. And then another edge to R, right? It's doable. Enum.map. So we call this, what this is, name and conditions. Have to output the name. Was it 3 arrows or 2 arrows? I don't remember. The condition text for each of the conditions. So this will have to be in a map, right? And then the target. Conditions. .map. I think we kept calling these case with a K. Now we do case, do. If we have condition, okay, we need to convert condition into a string. So condition is... Oh, the condition here, we can break it apart. This is always op, param, and value. So op is greater than this, and if it's less than, that's this. This returns a string. String is going to be param op value. This gives us a condition. In fact, I want this to be like this. We have a condition without. If we have a case without a condition, if we just have a target, then we output something similar, except without the condition, without the label. Okay. have this. You might as well just do it all here. So name. Now we have edges, I hope. This has to be a flat map. Okay. This probably needs to be in double quotes. Let's skip the double quotes. Now we do a join. Let's add a couple of spaces here. I never know if indentation is necessary in mermaid charts, but let's not risk it. Then we have then lines, and I have to say graph LR, new line, lines. Let's run, so now we pipe this into Keynote Mermaid. Okay. This is a lot prettier than I expected it to be. Now do we want to try this on full? We may. Let's try it out. Worst case, it crashes my browser. It evaluated very quickly, but now poor mermaid is trying to draw out this monstrosity. Yeah, there are a lot. Let's go back to example. Example is going to be a nicer thumbnail. Or should I have drawn this visualization while solving the problem? I don't think so, because at least I could mentally visualize this very easily. So it wouldn't really have helped. I guess it would have helped. Well, it would have helped at the very end when we had to go basically reverse this and say, okay, so to get to this A, we have to have an X that is less than this, an A that is less than this, and S that is less than this. Oh, and I just realized this isn't quite correct, is it? Yeah, no, this is actually wrong. Because the order of the match cases is important. So let's just do conditions with index. Let's just add an index and call it a day, because I don't really want to spend time trying to integrate the computation from part 2 into this visualization. We have name, then here we're also going to have IDX. Let's add another hash here. Okay, so now we can see that so it was actually displaying them in the right order. Okay, this is good enough. This is going to be the thumbnail. Now, let's have a quick look at stats. Everybody's solving today, right? 19. Yeah, it feels like more people than yesterday are solving today. Although, yes, people are struggling a bit on part 2, which is unsurprising. Part 2 is genuinely harder today. Part 2 required quite a bit of processing. Yeah, look at this. Looking back at part 2, bam, compute constraints, compute rule constraints, negate. Print constraints is unnecessary, but then group conditions and count possibilities, and the final processing here. This all took a bit of work. Alright, then that's it for today. Thank you for tuning in, and see you all tomorrow when we solve day 20. We have less than a week to go. This is exciting.